Hi everyone, welcome back. We're going to talk about linear regression models. But first, we're going to talk about correlation because it's going to set us up for understanding linear regression. And as we'll see, there's a relationship between correlation and linear regression. So this week, we're going to state what conditions are necessary to conduct a regression analysis, specifically a simple linear regression analysis, and then next time, multiple linear regression analysis. Discuss the use of controlling for variables in regression, interpret regression output, and also state the conditions necessary for multiple linear regression, where we have multiple independent variables. We'll also touch on the differences between MANOVA, ANCOVA, and MANCOVA as other multivariate techniques. But really our focus this week is on linear regression and multiple linear regression. And to do so, we're going to start off with a review of correlation. This is going to come back to us from the first week where we kind of thought of it more of as a descriptive statistic, where we were looking at the relationship between two variables and simply wanting to calculate some sort of index of their relationship. We weren't doing any formal hypothesis testing at that time when we discussed it before, nor were we making necessarily lots of checks on assumptions regarding linearity. But we're going to talk about that a little bit today, especially as we build up towards linear regression models, which is related to correlation. So as a review, a correlation coefficient is a statistic that summarizes the magnitude and direction of a linear relationship between the two variables. I want to emphasize here that it's measuring the strength of a linear relationship between two variables, not just any relationship. So if you recall, the Pearson's R is computed with variables that are interval or ratio level. And that includes both the X variable and the Y variable, are both on interval or ratio level scales. That allows us to look at how they are moving with respect to one another on their different scales. So a positive value for R represents a positive correlation. As the value of one variable goes up, the other goes up. A negative value would be where as one goes up, the other goes down, which will be easier to visualize once we see some scatter plots. But again, to review, the strength is indicated by the absolute value of R, which goes from -1 to +1, where 0 represents no relationship. And a value of -0.75 for R would be just as strong in magnitude as a positive 0.75. And we would say something that falls between -0.3 and 0.3 is either no relationship or a very weak relationship. Okay, so that's just review. But again, we were expressing an overall association between two variables using a standardized measure called the correlation coefficient. As we move into talking about linear regression, we're going to move away from using standardized coefficients, and our interpretation is going to be slightly different. However, we will still have positive and negative values for our coefficients, and so it's important to think about what these look like on a scatter plot. So for a value of R equals 0.4, notice that as values are going up on the x-axis, they're also going up on the y-axis. Take a moment to look at it if it's not instantly clear. But as we go up on X, as we move in this direction, values are also going up on Y. That's why we have a positive correlation coefficient. Likewise, over here, as values are going up on X, as we go to the right, they're actually coming down on the y-axis. So they're getting lower on the y-axis. That's why we then have a negative correlation coefficient. The strength has to do with how much spread there is around that best fitting line, which hasn't been drawn here, but your eyes are probably wanting to draw that best fitting line to this data. And you could imagine it falling somewhere in there. And the fact that they're spread around that line indicates the strength of association. Okay, so when we get to linear regression, we're still going to be talking about negative and positive relationships, but the coefficients that we compute in linear regression are going to be different. And they're going to be, in some ways, more useful and in some ways more limiting in our ability to make comparisons, especially in terms of the magnitude of relationships. One note is that we can do formal hypothesis testing with Pearson's R. We previously had discussed it mostly as a descriptive statistic to talk about the relationship between two variables. And often when we're doing exploratory analysis, we wouldn't bother to do a formal hypothesis test, but we certainly can. And so we can test for a linear association between two variables using hypothesis testing, just as we would with a t-test or ANOVA. In this case, the null hypothesis is that there's no correlation between the two variables in the population. Notice that the nomenclature is not R, but the equivalent for the population, which represents the true correlation in the population. So we're saying the null hypothesis is that there is no correlation between these two variables, and we then determine to what extent that is likely to be true given what we've observed in our data. Okay. So when we do hypothesis tests using R, there are some assumptions. One is that there's a normal distribution bivariately, which is a little hard to get your head around, but what that means is that for any given value of X, our Y values would be normally distributed around X. There's a similar assumption, which is that that spread, not just is it normally distributed, but the spread is similar at values of X. Okay, and you can use graphical techniques to assess this assumption. Mild violations of the assumption are often ignored, but if there's clearly deviations from this, it doesn't make sense to have some sort of summary measure. The relationship may be stronger at some levels of a variable and less strong at others, so it may not necessarily represent the true relationship. And likewise, our p-values are based on us having these assumptions in place. So again, magnitude with correlation can be expressed two ways. One, we can just simply report R, our Pearson's correlation coefficient, and that's readily interpretable, and we can compare correlation coefficients across different studies, across different variables within the same study. And so it's a really useful metric. Alternatively, we can report the coefficient of determination, which is Pearson's correlation squared, or little r squared. And that indicates the proportion of variability that is shared or explained by variability in the other variable. Again, these are interchangeable in the case of correlation, and it simply says how much are we explaining in terms of the relationship between these two variables, or how much of each variable are we explaining by having measured this other variable. Okay. This is going to come up when we get into linear regression, because we're going to have a similar measure, but the interpretation is slightly different. So linear regression is a technique that's used to analyze linear relationship between variables, just as correlation is. However, our orientation here is to make predictions about our dependent variable as a function of our independent variable in the case of simple linear regression. When we get to multiple linear regression, it'll be our dependent variable y as a function of multiple independent variables. But for a simple linear regression, where we have one dependent variable and one independent variable, correlation tests of hypothesis will be very similar to tests of coefficients in a linear regression model. But conceptually, they're different in that we are specifying that we are saying that one variable, our y or outcome, is a function of our x variable. In some ways, we're starting to move towards more of a causal type argument, but it's more just about the directionality of the relationship, that we're saying that y is related to x and that x precedes y. However, mathematically, and in terms of what p-values we would get, a hypothesis test regarding a correlation coefficient would be very similar to a p-value we would obtain from a simple linear regression model, but conceptually they're different. However, linear regression is ultimately going to be more powerful and can be used to make predictions about a dependent variable given more than one independent variable. which we'll discuss when we get to multiple regression during the next lesson. But we have to start with a simple linear regression. And so we can use simple linear regression to look at the association between a dependent variable and one independent variable. And often we'll run a series of these associations before putting them into a model. So we might have some outcome of interest, which won't change as we go from model to model, and then put in one at a time different independent variables to see what kind of crude association it has with our outcome, meaning just a bivariate relationship with the outcome. In a linear regression context, the independent variable is often called our predictor variable because we're using it to predict values of y based on our data. So in theory, we could have our model and fit a line to it, and we could then take values that aren't in our data, actually observed in our data, and predict what their outcome would be based on our model. Okay, so an example of this would be something like the Framingham study, where they developed a model to predict risk of heart disease within a certain time frame. And there's lots of different inputs you could have based on a patient's information. But if you know someone's blood pressure, if you know someone's BMI, if you know someone's age, each of those individually adds some prediction to the outcome. But ultimately, we're going to want to have some sort of multivariate model often because we know that there's not one causal factor. But simple regression is often used as an intermediate step to understand the relationships between two variables before moving on to multiple regression. The goal of regression is to fit a linear model to predict new values of y based on x. We're trying to create some sort of tool that we could use beyond our data to say something more generalizable about what's happening in the population. So before we get too far into looking at linear regression, we have to go back to our mathematics classes from elementary school or high school where we talked about the equation of a line. And we're not going to spend a lot of time on this, but if you recall, the equation of a line, y equals mx plus b, if we know the intercept denoted by here b, and we know the slope, we can draw a line. So in the context of regression, we're talking about linear regression, our y becomes values on one variable, whereas our x becomes values on another variable. We are also going to have a slope, and we're also going to have an intercept, just like with an equation of a line. It's slightly different, however, in terms of how we write this out, and also in terms of what we're really interested in interpreting information from these linear regression equations. So a linear regression equation looks very similar to an equation for a line, but our interpretation of it is a little bit different. So here we have y hat, which is our predicted value of a dependent variable y, as a function of some intercept constant alpha. So our intercept we also call a constant in the context of a linear regression model. Beta is the slope of the best fitting line. In the case of ordinary least squares regression, we're going to take the line that minimizes the sum of square differences of those points about the line in a scatter plot. There's also a random error term, which we don't often report out in our analysis. However, conceptually, there is this unexplained variability in y, not explained by our intercept and our x variable. Especially in the context of a simple linear regression model, we wouldn't expect to explain everything there is to know about y. There's going to be a lot of unmeasured variability in y. Some of it could be error, that is our inability to accurately measure either x or y, but also unmeasured confounders, unmeasurable confounders, all those things would be caught up in this error term. Ultimately, our goal is going to be to reduce that unexplained variability in y. So it's important to keep that in the back of your mind. When we actually calculate a predicted value of y, we would simply take the intercept plus the coefficient multiplied by the value that we have for that observation. So regression coefficients, unlike correlation coefficients, are in the original units of the variables. Specifically, a 1 unit change in x, our independent variable, results in a beta 1 change in our outcome y, where beta represents the regression coefficient. Okay, so as x increases by 1 unit, however x is measured, the beta tells us how much y will change in its original units. Okay. The use of original units in regression is both an advantage and a disadvantage. Clinically, we like to have things that can translate into real values. I mean, it's easily interpretable in that sense. However, it can be difficult to compare the strength of one variable and dependent variable relative to another variable and the dependent variable, given that they're measured in different units. So correlation is nice because it, again, is based on standardized units. Linear regression is always based on the original units. And just as a review, Pearson's correlation technically represents what we would expect in terms of a standard deviation change in one variable given a 1 standard deviation change in the other. So 1 standard deviation change in x is equal to a 0.75 standard deviation change in y if our Pearson's correlation is 0.75. The reverse is true as well. A 1 standard deviation change in y is equal to a 0.75 standard deviation in x. So it's kind of nifty that it's interchangeable and you can interpret it that way. Likewise, an r equals 0.75, if we're looking at other variables in relationship to x or in relation to y, we can kind of say the relative strength of association. Can't do that in linear regression. However, the benefits outweigh some of the downside of that. So here we can also use a scatter plot in linear regression to explore the relationship between two variables. Mind you, if we have too many points, too many observations, the scatter plot can look a little messy or look overfilled with points. But here we have a relatively small data set, and so we can visualize this. And what we have here is height plotted against weight. And in the context of linear regression, it's really important that we specify weight as our dependent variable and height as our independent variable. Okay, and the reason why we would do that is, in this case, biological and logical. We can't really think of height being a function of weight, but we can think of weight being a function of height. So though they're interchangeable in terms of understanding the relationship, as we move towards linear regression, we're going to want to have an outcome or a dependent variable that temporally comes after, like say, an exposure or some other kind of ordering, logical or causal ordering in terms of how we're thinking about it, okay? So given that equation for a linear regression model, in this case, a simple linear regression model, this is what our output will look like if we were to simply put weight as our dependent variable and height as our independent variable. This output might look a little different than what we're used to, but notice it has an intercept and it has a estimate for height. The estimate is our beta coefficient for height, meaning for a 1 unit change in height, so in this case, a 1 inch change in height, what would our expected difference be in terms of weight? So a 1 inch increase in height would be associated with a 4.146 increase in pounds. Again, it's in original units. And so we can use that to then say, well, if someone was 5 inches taller, we could multiply that coefficient by 5, and we would get a value of 20.5. So they would be 20.5 pounds heavier on average, based on this crude, simple model that we've developed so far that is explaining roughly 40 to 50% of the variability in weight, which we know from just running the correlation. The intercept value looks a little screwy. The intercept here is negative 92.7. Obviously, that's not a possible value for someone's predicted weight. The reason this happened or happens is that we're going well beyond our observed data. First of all, zero height really doesn't exist, so we shouldn't expect a reasonable value for our weight. However, if we were to extrapolate the line and go beyond our data, notice our data here, actually our lowest value is 50. Ideally, this axis would go all the way to 0, but you can see that our real observations go between roughly 50 inches and 75 inches, okay? We really shouldn't use the model to extrapolate beyond our observed highest and lowest values. It's really only good for that range of values. However, we do need that intercept. If we want to predict the actual weight of someone given X, we would take that intercept value, or our constant, and then add our height times whatever our observed value is. So if someone's 70 inches tall, it'll be 70 times 4, or 280. We add that to negative 92, and that would be the predicted weight. So it works out mathematically there, but it just doesn't work well for really, really small people that go beyond our data, okay? And we would probably want to develop a different model of the relationship between height and weight for, during gestation, for neonates, and for children. There may be a slightly different relationship. Here we're talking about relationship in adults. We can make our intercept interpretable or readily interpretable if we do what's called centering of our variables. That goes a little beyond this course, but we can actually make the intercept interpretable if we were to subtract the mean from height. That 0 would then represent a person of average height, in which case we'd have a predicted value for someone of average height. And so it would get out of the negative values. But again, so the units are in their original units. We wouldn't be able to reverse this and say if 1 unit change in y is associated with a 4.14 increase height in inches. The reverse does not hold true. We would have to rerun the model and put height as the outcome and weight as the independent variable if we wanted to know what that coefficient was. Okay, so just be careful of that. You can't interchange them like we could with the correlation coefficient. Notice that we also in this output have tests, and we have p-values associated with those tests. It's actually the ratio of the estimate to its standard error, and that gives us this t statistic from which we can derive a p-value. With linear regression, we're just going to let the software calculate actual p-value for us, but it is actually based on a t distribution. And not surprisingly, the null hypothesis would be that this estimate here is 0, that there's no relationship, that there's that our beta is 0, and the p-value says how likely is that to be true? How likely is that to be no relationship? Okay, so here we have notice also the value is positive. So we still have a positive relationship between height and weight. If we had a negative regression coefficient, that would suggest a negative linear relationship, which is equally interesting as a positive relationship. However, it's not constrained to fall between -1 and +1. It's going to be whatever the original units are. The goal of regression is to fit a model to our data. We create this best fitting line that minimizes the sum of square differences from that line. And we can then use that to predict values of y, even using values that fall outside our data. It should still be within the range of values for our x variable, but it doesn't necessarily actually have to exist in our data set. We could still use that line to predict some value of y, given any value of x that we wanted to plug into that equation. Keep in mind that a linear model is just one of many possible models. If our data does not conform to the assumptions of a linear model, one of which is that there's a linear relationship, then it doesn't make sense to use a linear model. So that's why the scatter plot is going to be important. If it doesn't look like there's a linear relationship, we may want to choose another fitting model, which kind of goes beyond this course. So there must be a linear relationship for it to be appropriate to do linear regression. We don't expect there to be a perfect fit to the data. We expect there to be that error, and it could be because of measurement error, it could be just that we haven't explained the phenomena. We need other variables, and that's what we're going to get to when we get to multiple linear regression. So in correlation, the nature and strength of a linear association, it's very useful for doing that. In linear regression, we are creating an equation that best describes that linear relationship between the variables, and we can then use it to predict other values of y given some value of x. Both can be used for hypothesis testing to determine if there's a statistically significant or non-zero linear relationship. And a simple linear regression is no more powerful than a correlation in terms of statistical tests. It's when we get to multiple linear regression that we start to get into a more powerful tool in terms of our ability to predict. So this is one of the more important points to consider again, is that the regression coefficient represents the predicted change in our dependent variable y given a 1 unit change in our independent variable x. In the example that we used, our beta coefficient of 4.15, a 1-inch increase in height predicts a 4.15 increase in pounds. If we wanted to have that coefficient expressed in tens of pounds or some other unit, we can simply change our units in the original data. But keep in mind, it's always going to represent a 1 unit change in our variable. So in summary, correlation and simple linear regression are very similar, and they have similar goals. However, the choice of method is based on study design and our conceptual understanding of the relationship between the two variables, and less about the level of the measurement. Also, we would often use simple linear regression as a way to build towards doing multiple linear regression, which is what we're going to cover next. So we'll often want to run simple linear regression models for each of our independent variables so that we can get a crude relationship between our outcome and our dependent, or get a crude relationship between our outcome and an independent variable so that we can see what happens to it in the context of a multivariate model. Also, please note that both correlation and linear regression have a ratio or interval level outcome measurement. Each approach has its advantages, and even though they're statistically very similar, and we can interpret p-values similarly in the case of a regression coefficient and a correlation coefficient, we're going to want to be mindful of those differences as we move forward because of the way in which we interpret the output. That we're talking about standardized units in the case of correlation and original units in the case of regression. There are ways to develop standardized coefficients in regression. That's often used in the social sciences. We don't do it as often in medical science or biomedical science. There's really no reason not to. It's just kind of by convention. And also in terms of interpretability, we also want to know what the actual predicted value is, but we can ask for from our software to create what are called standardized coefficients that do have the advantages of a correlation coefficient in the context of a regression model. That's all for this session. Next time, we're going to talk about multiple linear regression. Again, the only way to have these concepts come together is to practice and to do the exercises and to start running those models and seeing what your output looks like and interpreting that output. I recommend that you try running a correlation first and then looking at linear regression using the same variables and see what's similar and what's different between those two approaches. Thank you for listening. We'll talk again soon. Bye.